Alrighty, guys. So on the bell work, it says in state X, Mr. Camp's eighth grade class consisting of 26 students was surveyed, and 34.6% of the students reported that they had at least two siblings. Okay, the average eighth grade class size in the state is 26, so we don't really care about that information. The most important sentence is the one that comes up next. It says, if the students in Mr. Camp's class are representative of the students in the state's eighth grade classes, and there are 1,800 eighth grade classes in the state, which of the following best estimates the number of eighth grade students in the state who have fewer than two siblings? So picking out the important stuff, 26 and 34.6%, that is going to be huge because that gives us our benchmark. We don't really care that the average eighth grade class size in the state is 26. We just know that there are 1,800 eighth grade classes. Okay, or I guess the state is 26. So as long as those two add up, these two here, the students is, he has 26 in his class. The average in the state is 26. Okay, we can use this information to help give us a pretty decent estimate. Key thing to remember is that 1,800 doesn't mean the amount of students in the eighth grade. That's how many classes there are, right? So first thing we want to do is we want to figure out what 34.6% of 26 is. So if you plug into your calculator and you take 26 times 0.030 times 0.346, no O in front, you get about 8.996, or about 9 students. Okay, what does that mean? Well, it means that 9 students in each class reported that they have at least 2 siblings. Okay, so we can use this information. So if 9 say that they have 2 siblings, that means that 17 students don't, right? Because 9 plus 17 is 26, and you can't have a partial human being. That's why we round up to our whole, or we round to the next whole. Okay, so this information says that there are 17 students in each eighth grade class. That gives us, or that have 2 or more siblings. So if we take 17 and we multiply it by 1,800, we end up with 30,600, which is our answer. So the correct answer choice is answer C. All righty. So today what you have on tap is you have a lecture for the SAT next week. I'm going to take it easy on you. That way we can just make sure everybody can try their best that way and get the highest possible scores. So next week we won't have lecture. It'll just be like a homework activity on Monday, self-evaluations on Wednesday. Following week after that, we'll lecture 3-4. Week after that, we'll go 3-5. Then we have MAPS testing. Then we have 2 weeks of data collection so that I can have my good data. And we will call that pretty much a semester, especially for the seniors, since you guys get out a little earlier than everybody else. All right, off to lecture. So this is our 5-minute check over lesson 3.2. This is what we would have done 2 weeks ago. Okay, first one, it says evaluate log base 4 of the square root of 2. Okay, so a couple things here. We have log base 4, and remember, square root of 2. And we're going to alter it. Okay, we want to use our properties. First thing, how does 4 relate to 2? Well, if I take the square root of 4, that is going to be equal to 2, right? So 4 to the 1/2 is equal to 2, and I need to take the square root of 2. So that would be like 2 to the 1/2, right? So I can set it up, and I can replug in for this square root of 2 and rewrite it as log base 4 of 4 to the 1/2, which gives me 2, and then to the 1/2. That gives me the square root, because 4 to the 1/2 power is 2. And at this point, we have our power of a power property that kicks in, which says that it would be log base 4 of 4 to the 1/4. Okay, here we have one of our reciprocal properties of logarithms that state that if you have log base b and it's b to the x, our answer is going to be x. So in this case, our answer of log base 4 to 4 to the 1/4 is equal to 1/4. Okay, so applying a couple properties. Once again, remember the property that I just applied was log base b to the x is equal to x. Okay, that's one of the identity properties of the reciprocal property that comes into play. This one's a little tougher because you had to plug in a couple times and use power property of exponents to come out with the answer of 1/4. But nothing too terrible there. Let's look at the next one. Okay, so this one, evaluate log base 5 of 5. Okay, so you're asking yourself, what exponent would I have to raise 5 to get 5? Well, the answer to that is 1, because anything to the first power is just itself. So the only way to get 5 to stay 5 and apply a power to it is to have that power be 1. Okay, another one of your where your properties where it says log base b to the b is equal to 1. Okay, that's the only exponent that we can raise 5 to still get 5. Here we have another power property. We have 10 to the power of the common log of 2. Okay, the property that's going to kick in is b log b to the x is equal to x. So if we plug this in, we have 10. Common log always uses base 10. So in this case, since these two are the same base, 10 and the common log, it's just going to be equal to 2. There. That's because whenever we see it abbreviated as just log, we know that they are using 10 as the base. Different is if they're using the natural log, because then we use the natural base of e. But in this case, since it's common log, we know that this base is 10 here. Number 4, evaluate the natural log of -3. So in this situation, there are certain requirements that we need to have as a logarithm, which state that we cannot have a negative number here. Okay, it's one of the basic properties of logarithms. We cannot have a negative, or as a negative answer, you could call it. So this one, since this number is negative, we know it has to be d and being undefined. Sketch the graph of f of x equals the log of base 3 to the x. So if we're looking at this, this function is logarithmic growth, right? Because it's positive. So we want to find the answer choice that shows logarithmic growth. C is exponential growth. B is exponential decay. D is, that'd be logarithmic decay on D. The only one that shows logarithmic growth is answer choice A. So that makes that part pretty simple. And then we're analyzing the graph, okay, describe its domain, range, intercepts. So remember, the range is your y values. The range should not be cut off. Okay, the domain is cut off at 0 to a positive infinity because the y-axis is our asymptote. The intercepts, it should have an x-intercept at 1. The asymptotes is the y-axis. The end behavior is as x goes towards a positive infinity, f of x goes towards a positive infinity, and the limit as x goes towards a negative infinity, or as the limit as x approaches 0 from the right, it goes towards a negative infinity because our graph is kind of shaped like that, in which 0 being the asymptote, we can't really go towards a negative infinity on our domain. So looking through our answer choices here, it looks like our answer choice is going to be C. Okay, and that's because we have an increasing function. The domain, 0 to a positive infinity, that's true. Range, unlimited, all real numbers. X-intercept of 1, asymptote, y-axis. It's increasing from 0 to a positive infinity. It's perfect. In behavior here, that's perfect. And that's perfect as well. So any outstanding questions over 3-2? Today, it's going to be a little shorter, so I can handle a couple questions if you have them. That will be off and running. Oh, here's another one. Thought we were done with it, but I guess we weren't. Evaluate e to the natural log of x. Once again, this falls along with our power, or if we have a base where we have b to the log base b to the x, the answer is x. So in this case, our answer should be x because our natural base of e is the base that we're using for natural logs. Okay, so previously we evaluated logarithmic expressions with different bases. So just the key to remember is logarithms are all centered around chasing down exponents. We're trying to find the exponents and how they work. Today, what we're going to be talking about is we're going to apply some properties of logarithms. Okay, what these properties do is they rewrite equations. They make them simpler to handle. Okay, that way some of your properties can apply. And then we're going to apply the change of base formula. The change of base formula, it allows you to evaluate logarithms with different bases using a calculator. Okay, that's the whole purpose of the change of base. Properties of logarithms are pretty simple. You've seen a lot of them before, or they kind of make sense. So if bx and y are positive real numbers and b cannot equal 1 and p is a real number, then the following statements are true. I don't know why. Oh, p brings in the exponents. So the first one is the product property of logarithms. This one's kind of like the power property or the product property of radicals. It allows us to split them up and then alter. Okay, like when we were taking the square roots and we were trying to find the exact answer, they would give us a number underneath the radical and then we'd be able to split that. We can do this same thing here. So you see you have log base b of xy, and x and y are multiplied with each other. This is equivalent to the log base b of x plus the log base b of y. So using the product property, whenever they are multiplied, we can separate them and use addition. Okay, we can separate them and use addition. The key is X and Y are factors. Okay. The next one that you have is the quotient property, kind of the same thing as the quotient property of radicals. Says the log base b of x divided by y is equal to the log base b of x minus the log base b of y. Okay, so it's kind of the same thing as the product property, except for we have division, so we can separate those using subtraction. Okay, and then the final one, the power property. So it's the log base b of x to the p is equal to p times the log of b to the x. So more or less what the power property does is it takes the exponent out and puts it in front. Okay, this is handy because we can separate the exponents and then we're just dealing with really a multiplication problem at that point. So I'll give you a couple seconds to write those down. We will be using all of these, especially in expanding and condensing. But overall, it's not the most difficult thing in the world. Wait for my clock to hit 8:52. Multiply, add, divided, subtract. It's an exponent. You can bring it out in front. Perfect, 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 perfect. All right, let's see how these properties are applied. So here we want to use the properties of logarithms, and we want to express the log base 10, because that's common log, of 96 in terms of log base 10 of 2 and log base 10 of 3. So we're going to use these, and your properties will write them out like this. So we want to figure out how do 2 and 3 apply to get 96. Okay, so let's start thinking of some factors of 96. Okay, 96 can be broken down into 1 and 96. It can be broken down to 2 and 48. It can be broken down into 3 and 32. Okay, I like these numbers, 3 and 32. And the reason I like 3 and 32 is because 32 can be rewritten or is equivalent to 2 to the 5th. Right? So this log of 96 is really the log of 3 times 2 to the 5th. Right? Or 3 times 32. Okay, I can use these and I can apply my power property or my product property, and now I can split those. So I can set it up as its log of 3 plus the log of 2 to the 5th. Okay, you would think that at this point it's done. Wow, I'm struggling to write right now. Sorry, I'll get better. But at this point, it's really not quite done yet. What we want to do is we want to use the power property of logarithms and bring this exponent out to the front. Okay, so our final answer is going to be the log of 3 plus 5 times the log of 2. Okay, and the reason, the hardest part about this was really selecting my numbers. I have to select numbers that fit with what was given me. It said for me to express it in terms of log of 2 and log of 3. So that's why I came up with 3 and 32, because I knew that 2 to the 5th is 32, right? And 3 is going to be just itself, 3 to the first power. So once I'm expanding them, I can use them to simplify. Okay, but the hardest part of that was finding what numbers actually correspond to the answer to how they want it. Okay, so log of 96 is equal to 2 to the 5th times the log times 3. Okay, and then they're going to split them using the product property of logarithms. Okay, and then the last thing that we had to do is bring that exponent out front, which comes from the power property. So 5 log of 2 plus log of 3. These can be, it's just like with regular multiplication, either way, whichever one's in front, you would still get the same answer. But that is going to be our answer right there. So you can see we use the product property and we use the power property there. Or our next one. Okay, so here we're expressing the log of 32 divided by 9, and we're looking in terms of log of 2 and log of 3. So how do these two numbers relate? Well, we just found out that 32 is 2 to the 5th, right? And we know that 3 squared is 9. So the first thing that I want to do is I'm going to take this log of 32 divided by 9, and I'm going to change it into the log of 2 to the 5th over 3 squared. Okay, now I've got my numbers. Now I can use the quotient property, which allows me to split these and put subtraction in the middle. So that's the log of 2 to the 5th minus the log of 3 squared. And the last part is to bring my exponents out front using the product or the power property of logarithms. So it's 5 log of 2 minus 2 log of 3. This one we have to be exact, okay, because it started out as 32 divided by 9. So we have to have order matters with subtraction, right? Order matters with subtraction and division. Order does not matter with multiplication and addition. Okay, that's because as long as you're adding, it doesn't matter what you add first. But if you're subtracting, you can get a completely different altered number. So they actually did the quotient property first. Then they put log of 2 to the 5th, log of 3 squared. And then 5 log of 2 minus 2 log of 3. You can see I did it just a little bit different in the order, but I still arrived at the same answer as 5 log of 2 minus 2 log of 3. Right there. Okay, so this one is going to be a little tougher. We're expressing the natural log of 125 divided by 27 in terms of the natural log of 3 and the natural log of 5. Okay, remember our base is E here. Okay, so really I just want to figure out how do these really relate to each other? Well, I know off the top of my head that 27 is 3 cubed, because 3 times 3 is 9, times 3 again gives me 27. So this is 3 cubed. 125 as it correlates to natural log of 5 or just 5. That's going to be 5 cubed as well. 5 times 5 is 25, times 5 again gives me 125. Okay, so what I would do is I can split these first using the quotient property. Okay, and once I split them with the quotient property, I'm going to be left with the natural log of 125 minus the natural log of 27. Then I would plug in natural log, that's going to be 5 cubed minus the natural log of 3 cubed. Okay, now I can use the power property to bring the exponents out front. So that's 3 natural log of 5 minus 3 natural log of 3. Okay, and these are just asking us to express it. So my answer in this case should be C. Perfect, 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 perfect. Okay, these ones aren't very difficult. They will give you the terms at which they want you to express them. All right, it'll always be like expressing the natural log of 2 and natural log of 5. All right, I believe it's 7 and 4 are the ones that your problems correspond to. But you can see it's a lot of just reworking it. This is also kind of referred to as expanding. Okay, now we're going to use these properties to simplify them. Okay, so we're evaluating. So we have the log base 2 of the cube root of 32. Okay, so here we're going to use our properties to get it into a more manageable format. So we know that 2 to the 5th is 32. So I have the log base 2 of the cube root of 32. Okay, first thing I'm going to do is I'm going to rework this. Okay, so I'm going to change that into the log of base 2 of the cube root of 2 to the 5th. Just like that. Next thing I'm going to do is I'm going to remove my radical using the properties of rational exponents. I know that if it's the cube root, it's really this to the power of 1/3. So now I have log base 2 of 2 to the 5th to the 1/3. Now I can use my power of a power property of exponents and multiply those so that I get the log base 2 of 2 to the 5/3, just like that. Okay, and that's because power of a power. So I have 2 to the power of 5 to the power of 1/3. That allows me to multiply those exponents. That's how I got 5/3. Okay, now this corresponds to your reciprocal property, which states that the log base b of b to the x is equal to the x. Okay, does this fit? Yes, it does. I have the log base 2 of 2 to the 5/3. Therefore, my answer is going to be my exponent of 5/3. Just like so. Another thing I could have done, or a different way of treating it, rather than using this property, I still have to use another property, even though we know that it's going to be 5/3. What I could have done is I could have used the power property of exponents, brought this 5/3 out front as the times of log base 2 of 2. Well, log base 2 of 2 is 1. 5/3 times 1 still gives me 5/3. Okay, so two different ways I could use it. In either case, I had to get it into a base of 2, and that's why I used 2 to the 5th. Okay, so here they rewrote it using rational exponents first. That's more than fine. Then they plugged in 2 to the 5th, since that is equivalent to 32. Power property of exponents, so they multiply this 5 times 1/3. So they get 5/3. Power property of logarithms, they bring it out front. The log of 2 to the log base 2 of 2 is 1. So 5/3 times 1 or 5/3. That's because our answer is 5/3. So you can see how these properties kind of they interwork. It's not the most difficult process, it's different. So we have to pay attention, be very detailed as we're going through this. Ooh, this will be a good one. Okay, so evaluate 3 times the natural log of e to the 4th minus 2 times the natural log of e squared. So first thing, I'm going to write it down. So I get 3 natural log of e to the 4th minus 2 natural log of e squared. Okay, so it looks like it should be a pretty complex problem, but in all reality, it's really not. Okay, first thing I'm going to do is I'm going to use the power property of logarithms. I'm going to bring my exponents. So this e to the 4th, that's going to come out front. E squared is going to come out front. What that's going to leave me with is 4, this exponent, times a quantity of 3 natural log of e. Okay, and that's still going to be minus 2 times the natural log of e. Okay, so at this point I'm going to distribute. Okay, I can only distribute to my constants that are out front. 4 times 3 is 12. So this is 12 natural log of e minus 2 times 2 is 4. It's 4 natural log of e. And remember, these are multiplied. So here we have a property again where it's the natural log of e is always equal to 1. That's because our base of the natural log is e. So what power could I raise e to get e? The answer to that has to be 1. So this is really 12 times 1 minus 4 times 1. 12 times 1 is 12. 4 times 1 is 4. So 12 minus 4 is equal to 8. So power properties of logarithms, they bring the exponents out front. So this 4 comes here, this 2 comes here, and they multiply. So 12 natural log of e minus 4 natural log of e. The natural log of e is 1, right? So 12 times 1 minus 4 times 1 is 8. So you can see it started out as looking very complex, right? At the beginning, it looks tough, but I can sort through it using my properties and the properties that we know from 3.2 and turn it into a pretty simple problem. Okay, here's another good one. Evaluate the log base 3 of 81, the cube root of 81. This will be fun. All right, first thing, right problem. Log base 3 of the cube root of 81. So first thing, I'm going to use rational exponents. So that gives me log base 3 of 81 to the 1/3, because that's the cube root of rational exponents. Okay, now the next thing I got to ask myself is how could I get 81 into a base of 3? Well, 3 times 3 is 9, times 3 again is 27, times 3 again is 81. So this 81 is equivalent to 3 to the 4th, right? Squared, cubed, yeah. So we can rewrite it as the log base 3 of 3 to the 4th to the 1/3. Now I use my power property, which gives me log of base 3 of 3 to the 4/3. Okay, then I know that log base 3 of 3, that's 1. 4/3 would be out front, or I could use my reciprocal property. But my answer is going to be 4/3. Ooh, fun. Okay. Now the next type of problems, they're going to ask you to expand these. Whenever you see expand, we're not looking to evaluate. We're not looking to simplify. Okay. We're not looking to solve it. We're just looking to expand it. That means take it from this condensed format and expand it all the way out. This is where your power property of logarithms and your quotient property of logarithms really take full effect. Okay. So I have a natural log of 4m cubed into the 5th. Okay, the first thing you got to realize is that these are all multiplied together. Okay, it's the natural log of 4 times n cubed times n to the 5th. Okay, so the first thing I want to do is I want to use my power property of logarithms and break those all apart. So this is equivalent to the natural log of 4 plus the natural log of m cubed plus the natural log of n to the 5th. Okay, so now I've got it expanded a little bit. The next thing I have to do is I have to use my power property of logarithms and bring these exponents out front. So my final answer, and its full expanded version, is the natural log of 4 plus 3 natural log of m plus 5 natural log of n. Okay, and that is my expanded format. Okay, understand that when the directions tell you to expand it, they're not looking for you to solve it. They're looking for you to expand it out. Okay, that way we get comfortable with expanding these. That way we can use some properties to help apply or to help us evaluate them. So here they use the product property of logarithms to expand them all out. And that's because it was 4 times n cubed times n to the 5th. Okay, now they're going to use the power property and bring those exponents out front. And that's as far as we can expand it. Okay, and we got to pay attention to what the directions tell us to. It asks for us to expand it, not evaluate. Oh, this one looks like fun. Okay. So we're expanding the common log of 2x minus 3 divided by 3 times the cube, the 4th root of x. Okay, so the first thing I want to do is I want to examine this. What parts could I really expand? I know I can use the quotient property to set these up as a subtraction right there. Okay, but if you pay attention to this 2x minus 3, that's subtracted, so that's a whole quantity. I can't split up 2x minus 3. That has to stay. Okay, but this 3 times the fourth root of x, I can expand that, right? Because that's multiplication. I have a property that allows me to expand that. I don't have a property that allows me to expand the subtraction here. Okay, so this 2x minus 3 has to stay. I'm going to have a subtraction, and then I'm going to have a addition. Okay, so first thing, I'm going to write it. So the log of 2x minus 3 divided by 3 times the fourth root of x. Okay, first property I'm going to use, quotient property. Says that the log of 2x minus 3, that's going to stay together as a quantity, minus the log of 3 fourth root of x. Okay, so this part's done. Can't do anything with that, right? It's this part. This 3 times the fourth root of x, that can be expanded by the product property. So once I do that, I'm left with the log of 2x minus 3 minus the log of 3 plus the log of the fourth root of x. Okay, so looking at it, seems like I've got it all separated out. However, since it's the fourth root of x, remember that's really x to the 1/4, right? Fourth root of x through rational exponents, that's x to the 1/4. They're equivalent, right? So now the last part would be to use the power property and bring this exponent out front, which leaves me my final answer of log 2x minus 3 as a quantity minus the log of 3 plus 1/4 the log of x. Bang. Done and done. Okay, so there's the quotient property. That's the first split. That's what gave me the subtraction. Now the product property separates those two. Okay, now they're going to use rational exponents because the fourth root of x is really x to the 1/4 power. Okay, and then they're going to bring that exponent out front using the power property. And that is our final answer. All right. So looking at this one, I'm not going to do this all together. I guess I could. Okay, so expand the natural log of x cubed divided by the square root of x minus 7. So once again, I want to analyze this one and figure out what can be expanded, what can't. Okay, this square root of x minus 7, I can't do anything with the x minus 7. They have to stay together. So first part, quotient property. So that's the natural log of x cubed minus the natural log of square root of x minus 7. Then I'm going to use rational exponents to get natural log of x cubed minus the natural log quantity of x minus 7 to the 1/2 power. Then I'm going to bring them out front using the power property logarithms to get 3 natural log of x minus 1/2 the natural log of x minus 7. And I couldn't do anything with the x minus 7 because those are subtracted, right? I don't have a property that applies to that. So my final answer should be A. Okay, so now you know how to expand them. The last part, or the next part, not the last part, because we still got the change of base formula to go through, is to condense them, which is basically to reverse everything that we just had. So we're condensing 1/2 log base 4 of x minus 3 log base 4 of x minus 2. Okay, and the goal is to get it into one logarithm. So we're condensing it all back down. So I have 1/2 log 4 of x minus 3 log of 4 x minus 2. Okay, first thing I want to do is I want to reverse my power property, okay, which brought my exponents out front. Now they're going to be back to the front, back inside the logarithm. So after I do that, I'm going to have the log base 4 of x to the 1/2, which is really the square root, minus log base 4 of x minus 2 cubed. Okay, now I'm going to use rational exponents to get those back, to get this x to the 1/2 power to the square root. So that's log base 4 of the square root of x minus log base 4 of x minus 2 cubed. Last thing is to reverse the quotient property, which puts this on top of this. So it will be log base 4 of the square root of x divided by x minus 2 cubed. Yep, looks good. Looks good, looks good, looks good. So condensing is they give you the expanded format and you push it all back together. Expanding is they give you the condensed format and you expand it out. In case you are curious on what expand and condense mean. Okay, so there's the power property where they took what was out front and put them back as exponents. Then they do the quotient property. I don't know why they did that. Now they reverse rational exponents. One second. I don't know why they left it as 1. Yeah, that's that was just weird looking at that one. I don't like the way they did that. How they have the log base 4 of the square root of x over the log base 4 of x minus 2 cubed. You have the same base. Quotient property states that it can be written as log base 4 of the square root of x divided by x squared minus 2, and that's what I was double checking. See, right there. It can be condensed into one logarithm rather than a logarithm divided by another logarithm. I don't like that. They just do it very difficultly. The key thing is all these properties, like if we were looking at them, especially the power, the product, and the quotient property, understand those have the same base. Okay, they have to have the same base to be able to be expanded and condensed. So the product property log base b of xy can be split into log base b of x plus log base b of y, right? You don't have to, they have to have the same base in order to comply with the property. That's why I don't understand why they did that. They should have just left it as log base 4. But I didn't write the book. I just utilize it. Okay, so we're condensing the natural log of x plus 1 or 5 natural log of x plus 1 plus x plus 6 natural log of x. So 5 natural log of x plus 1 plus 6 natural log of x. Okay, this one, the properties do apply because I'm using the natural log on both. So I have the consistent base of t. So no problems there. All righty. So first step, let's reverse the power property. So this one, the first one is going to turn in the natural log of x plus 1 to the 5th power plus the natural log of x to the 6th. Okay, now I can use my power property or my product property of logarithms to condense these into one, which would be the natural log of x plus 1 to the 5th x to the 6th. Pretty simple. So first step, power property, bringing those exponents from out front. And then they use the product property. Just remember, order does not matter with multiplication. It only matters with division and subtraction. So I had the natural log of x plus 1 to the 5th first, then x to the 6th. That's more than fine. Okay, so this one's probably actually one of the tougher ones. And I don't like that it's the multiple choice question. So here we're condensing the negative natural log of x squared. Okay, since there's a negative out front, this corresponds to the quotient property. Okay, these two are going to be multiplied together. And this is on the bottom, this natural log of x squared. So it's the negative natural log of x squared plus natural log of x plus 3 plus natural log of x. Okay, they all have the same base, so I'm good. So it's these two are going to be multiplied with this one on the denominator. Okay, so I'm going to, because the power property corresponds to this one, or the product property corresponds to these two, quotient property corresponds to this one. Okay, that's why it has the negative out front. That's signifying that this is in the denominator. Okay, so once I combine all these together, I get the natural log of x, that's this one, times x plus 3, that's that one, over x squared, that's this one. Now I can simplify this. Okay, I have an x on the outside of the parentheses, and I have two x's on the bottom. That means that this would really just turn into being the natural log of x plus 3 over x. So I have one x in the top, two x's in the bottom. So I can alleviate those because they are redundant. I just had parentheses around my numerator. All right, here is probably the most helpful formula that you would need, especially when it's considered logarithms. What this does is it allows you to take and use the calculator on logarithms that are different than the natural log and the common log. So it allows you to use your calculator. Okay, I'll give you a second to get that all typed in, or maybe I won't because I was trying to get my calculator up. Just give me 1 second. So that's what I wanted. Start that bad boy, get her all fired up. Go back to this bad boy. There's your property again. Okay, so what it says is for any positive real numbers a, b, and x, where a cannot equal 1, b cannot equal 1, we can find the actual evaluations of this as by taking the log base b of x is equivalent to the log base a of x and log base a of b. Okay, now when I'm doing this, if you look, so the base was b, that becomes the answer of my second logarithm, and x becomes the answer of my first one. What I want to do is I want to select actual logarithms that I can plug into the calculator. So for this, I am always going to be using the common log or the natural log. Okay, so this would be the common log of x divided by the common log of b, or the natural log of x divided by the natural log of b. Okay, but you see how it's b to the x, and then b, we're just plugging it in there, and you'll be able to see it on our next problem. Okay, so evaluate log base 6 of 4. Okay, it's not a common log, it's not the natural log, so naturally we wouldn't be able to really solve this. Like, it would be very tough to figure out the exponent that we would have to raise 6 to get 4, right? That really wouldn't work. Okay, you can't really do that mentally. This is where the change of base formula comes in. So since it's log base 6 of 4, okay, this is equivalent to, I'm going to use the common log, the log of 4 divided by the log of 6 as common logs. Get my calculator up. I just had it. And then once I've done that, I can just plug it into the calculator. So I have the log, common log of 4 divided by the common log of 6. You can see my answer is 0.774. So I'm going to round it to this third decimal place. So 0.774 is my answer. And if you wanted to check that on a calculator, you could actually do that. You could say 6 to the, oh, crap. I'll get their answer first. I messed up. So you can see they plugged it in the change of base formula. Then they plugged it into a calculator. They get 0.77. So let's see if this is correct. So if we take 6 to the power of 0.77, you can see we get 3.97. That would be rounded up to 4. I think it was 0.774. See, once I figured out that third decimal place, now I'm even farther, or now I'm even closer to 4. So the change of base formula, it allows you to find those exponents using a calculator. Okay, but the key is log of 4 is on the top, log of 6 is on the bottom. And you can use the natural log too. So like this one, log of base 1/3 of 8. So this is going to be, I'll use natural log on this one. Where is it? Where is natural log? Found it, now I forgot my numbers. 8 1/3. So the natural log, I'll clear it, dang it. The natural log of 8 divided by the natural log of 1 divided by 3. You can see I get -1.892. So -1.893. But this is all calculator driven. I just carried out to that third decimal place. Okay, this one makes sense to have a negative answer because the only way you'd get an actual positive or a non-fraction is if you raise 1/3 to a negative exponent. That way it's reciprocal exponents and the 3 becomes on top. So here, once again, we're going to use a change of base formula. And that is the natural log of 25 divided by the natural log of 1/5. Plug it all in, hit enter. See, we get -2. And our answer is -2. All righty, so that's what I have for you guys. Now you're off, or you're going to be off working on your homework. It's a little bit longer assignment. I think it's about 28 problems, but it's because a lot of them are just reworking them. You're going to expand, you can condense, and then I think the last 12 or 14 is all using the change of base formula, which is all calculator driven. You can use that meta calculator, or you can use a TI-83 if you have one, but it'll be evaluating, expanding, and simplifying